welcome to another module in this massive open online course. We are looking at the group and phase delay. Let us continue our discussion. So, we have the group and phase delay all right, and before that let me just correct a minor error, that is this should be h of omega h, and therefore, the net output of the LTI system corresponding to this signal, this modulated message signal, remember that is what we are looking at, a cosine omega m t into cosine omega naught t, that is given as a by 2 net output equals a by 2 magnitude h of omega, magnitude h of omega I think L times cosine omega L t plus phi omega L plus a by 2 magnitude h of omega h cosine omega h t plus phi of omega h. And now we have said that these two quantities, magnitude h of omega L is approximately equal to, correct, magnitude h of omega L approximately equal to magnitude h of omega h is approximately, both of these are approximately equal to magnitude h of omega naught, because omega m is very small, correct. So, the spacing between omega L and omega h is very small, that is 2 omega m, which is much smaller compared to the carrier frequency omega naught, okay. And therefore, this is approximately equal to a by 2 magnitude h of omega naught cosine omega L t plus phi omega L plus a by 2 magnitude h of omega h cosine omega h t plus phi omega h, which is equal to, now you can simplify this as a by 2 or a by 2 into 2. So, we have, I am sorry, this is cosine omega naught, a by 2, this is 2 a to a by 2, that is a magnitude h of omega naught cosine omega h minus omega L by 2 into t plus phi of omega h minus phi of omega t divided by 2 times cosine of omega h plus omega L divided by 2 plus, that is, this is cosine A plus cosine B is twice cosine A minus B by 2 to cosine A plus B by 2. So, that is phi of omega h plus phi of omega L divided by 2. Okay. Now, if you see this, if you check this, you have omega h equals omega naught plus omega m, omega L equals omega naught minus omega m. This implies omega h plus omega naught by omega h plus omega L by 2 plus omega h by 2 equals omega naught, and omega h minus omega L by 2 equals omega m. So, which means that this can be simplified, that this quantity here can be simplified as a by 2 cosine omega L plus omega h by 2, or what is the first quantity, omega h minus omega L by 2, correct. So, phi h of omega, so that is cosine of omega m t plus phi of omega h minus phi of omega L divided by 2 times cosine of omega h plus omega L by 2, that is omega naught t plus phi of omega h plus phi of omega L divided by 2. Okay. Now, what we are going to do, because since omega m is small, correct. So, basically we are considering a small neighborhood around the carrier frequency omega naught. So, we can use Taylor series expansion to simplify this phase function phi, alright, because the message frequency omega m is much smaller than the carrier frequency omega naught. So, we have phi of omega plus delta omega, phi of omega naught plus delta omega for small delta omega is approximately equal to phi of omega naught plus d phi by d omega evaluated at omega equal to omega naught into delta omega. This we know is the well known Taylor series approximation, first order Taylor series approximation. Okay. This is the Taylor series approximation, which implies the net output can be simplified as, let us look at phi of omega h. Now, phi of omega h you can see is phi of omega naught plus, well, omega m, which is approximately equal to, again using the Taylor series approximation, this is approximately equal to phi of omega naught plus the derivative phi prime omega naught, derivative at omega naught times omega m, correct, and phi of omega L, this is equal to phi of omega naught minus omega m, which is approximately equal to phi of omega naught minus phi prime omega naught into omega m. Okay. So, these two relations we have obtained using the Taylor series approximation, and therefore, this implies now using these Taylor series approximations we can evaluate phi of omega h plus phi of omega L by 2 and phi of omega h minus phi of omega L divided by 2 approximately. Okay. So, this implies phi of omega h, well, the first one is standard, phi of omega h plus phi of omega L divided by 2, that you can see is approximately equal to phi of omega naught, and more interestingly phi of omega h minus phi of omega L divided by 2, this is approximately equal to phi prime omega naught into omega m, that is basically your d phi by d omega evaluated at omega into equal to omega naught times omega m. Okay. So, this is your phi of omega h phi of omega h minus phi of omega L by 2. Now, substituting these, now we take these relations for approximate relations for phi of omega h plus phi of omega L by 2 and phi of omega h minus phi of omega L by 2, and substitute these in the expression for the net output. Okay, and that yields the net output is now approximately A Substituting these expressions, we have it, this is equal to A magnitude h of omega naught cosine omega mt, correct, cosine omega mt plus phi h minus phi l by 2, that is we can see have seen d phi by d omega at omega equal to omega naught into omega m, okay, times you have something interesting, that is cosine omega c t plus this is your simple phi of omega naught, that is omega h plus omega l by 2, which is equal to, now you can simplify this as A magnitude h of omega naught cosine omega m t minus, I am going to simply write this as phi prime omega naught, correct, not minus or plus phi prime omega naught times cosine omega naught t plus phi of omega naught divided by omega naught. And we know that this quantity is basically, this quantity is your minus tau p, this is equal to the phase delay, and this quantity that you see here, that is the delay of the message signal, this is now your group delay, right. So, you have your phase delay and group delay. So, you can write this resulting output as A magnitude h of omega naught cosine omega m t minus tau g, where tau g is the group delay, times cosine of omega naught t minus tau p, and therefore, tau g is the group delay minus d phi omega over d omega evaluated at omega equal to omega naught, that is your group delay, and tau p of omega naught equals minus phi of omega naught divided by omega naught. Okay. These are the group and phase delay expressions. So, these are the group and phase delay expressions, and this is very important. So, this is your group delay, and this is your phase delay. And what is very interesting is that when you pass this LTI system with the impulse response h t, all right, and frequency response h omega, phase response phi omega, the envelope, that is the message, is delayed by the group delay, correct, that is tau g of omega, that is minus d phi omega over d omega evaluated at omega equal to omega naught, and the carrier is delayed by phi omega naught divided by omega naught, and these are the group and phase delays. Okay. So, what you can see is that the message is delayed by the group delay or the envelope, message delayed by the group delay tau g, and the carrier, as usual, as we have seen before, carrier is delayed by the narrowband message is delayed by the group delay, and the carrier is delayed by the phase delay. And further, if the phase is linear, that is which implies phi of omega equals k omega. Now, look at this, the phase delay tau p of omega equals, well, phi of omega divided by, or tau p of omega naught equals phi of omega divided by omega naught equals k, or minus phi of omega naught divided by phi of omega naught is k, is minus k, and also the phase delay or the group delay tau g of omega naught is minus d phi omega by d omega evaluated at omega equals omega naught, and this is also equal to minus k, which implies for a linear phase tau p of omega, any omega for that matter, is tau g of omega. This implies that the phase delay equals the group delay. Okay. That is for a modulated narrow band message signal, for a narrow band modulated message signal, correct. When you pass it through an LTI system, that is, if the LTI system has a linear phase characteristic, then the phase delay is equal to the group delay. All right. Okay. Let us do a simple example to understand this better. Example for the group and phase delay. Okay. And consider an RC circuit. With the standard serial RC circuit that we have. So, this is R, this is C, and this is your output voltage, this is your input voltage that has VIT, the output voltage V0t. Now, we know that the transfer function, okay. Now, what we want to do for this is at f equal to 100 hertz, and we are given that R is equal to 1 kilo ohm and C is equal to 1 microfarad. We want to derive what is the group delay. All right. So, what is the group delay for this serial RC circuit with output across the capacitor with given a 1 kilo ohm resistance and capacitance is 1 microfarad. Okay. Now, we know that the transfer function of this is simply, that is 1 over the impedance of the capacitor divided by 1 over divided by R plus 1 over impedance of the capacitor, that is j omega c, which is 1 over 1 plus j omega r c. Now, you can see R c is equal to 10 to the power of R c is equal to 1 kilo ohm into 1 microfarad equals 10 to the power of minus 3, in fact the units is seconds. Okay. And therefore, now if you look at h of omega, now if you see h of omega, the transfer function, this is your h of omega, Now, if you see, so h of omega equals the transfer function 1 over 1 plus j omega r c. So, if you look at the phase of omega, this will be minus tan inverse omega r c, because the phase of 1 plus j omega r c is tan inverse omega r c, all right, and but that is in the denominator. So, the net phase is minus tan inverse omega r c, and therefore, the group delay tau g, the group delay equals minus d phi omega as a function of omega minus d phi omega over d omega, that is tan inverse omega r c, derivative of tan inverse omega r c, which is basically, well, r c divided by 1 plus omega square r square c square, which is equal to, now substitute the values of r c, 1 kilo ohm into 1 microfarad. We know, well, we know the value of R c, but anyway 1 kilo ohm into 1 microfarad divided by 1 plus frequency is given as 100 hertz. So, omega equals 2 pi into 100, okay, square into 1 kilo ohm R c square into 1 microfarad square, okay. So, that is what you get net, and that evaluates to basically 0.717 milliseconds, okay. And this is, remember, at f equals 100 hertz or omega equals 2 pi into 100, that is 200 pi radians per second. So, this illustrates the group delay calculation for a simple example. All right. So, in this module what we have done is basically we have completed our discussion on the group delay, demonstrated a very interesting aspect, that is when you pass a modulated message signal through an LTI system with the message signal, correct, narrowband modulation, where the message signal frequency is much smaller than the carrier frequency, then one can approximate the output signal as the message being delayed by the group delay while the carrier being delayed by the phase delay. And we have calculated this group delay and phase delay for a linear system. We have shown that these both are equal. For a simple RC circuit, which is basically a non-ideal low pass filter, we have evaluated this and demonstrated how to evaluate the group and phase delay at a given frequency. All right, so we will stop here and continue in the subsequent module. Thank you very much.